This would be the class that was scheduled for Monday, April 20th. Now, what I'm doing is like it says there, starting section 13. Since Friday's exam is only sections 1 through 12, I can see how it would be entirely reasonable to maybe wait a few days to watch this instead of doing it on the 20th, but I'm just going by what the original schedule was from the beginning of the semester. So whenever it seems like the most reasonable time to you is when you can actually watch this. But anyhow, we are done with electricity and magnetism after what seems like a very long time. The last two sections of the course are a look at the laws of thermodynamics. We had started talking about heat and temperature in physics 131. And I mean, I've got reasons for this, but the way it works out is that we start on heat and temperature and thermal physics like at the end of November, and then I give you something like 4 months to completely forget everything I said, and then I pick up where I left off and do a little more of that sort of thing at the end of this course. So there really isn't any perfect way to do things, and this is one of the weak spots in my approach, I guess. So review of the things that you probably forgot from, well, maybe not, let's hope not. Especially the gas law is going to be popping up frequently as we go along here. An ideal gas, remember, is a set of point-like, well, it's a set of molecules made of point-like atoms which do not interact with each other in any way except maybe to collide once in a while, but there's no intermolecular forces aside from that. Remember that both the pressure and temperature are absolute. If you are given gauge pressure, which is frequently what people read off of pressure gauges, you have to add 1 atmosphere. And if you're given degrees Celsius, you have to convert to Kelvin. And I guess the rest of that's pretty straightforward. So there are 4 laws of thermodynamics altogether, which rather oddly are numbered 0 through 3 rather than 1 through 4. The 2 most important ones are the first and the second laws, and we're going to mostly focus on those. Section 13 deals with the first law together with various related issues, and section 14 deals with the second law together with various related issues. The first law is not really an entirely new concept. It's our old friend conservation of energy, really. You have this very general principle of conservation of energy, and after I had sort of introduced that last fall, I said, now, if you take that and phrase it in a way that's convenient for solving problems in mechanics, you have what's called the work energy theorem. And we use that to do various sorts of things. Well, if you take conservation of energy and phrase it in a different way, which is useful for problems in thermodynamics, you have this. Delta E int stands for the change in the system's internal energy. Now, maybe I should give you a brief explanation for what that means before I go any further. It's a little further down the page here. Internal energy add up all forms of energy possessed by the system's molecules relative to its center of mass. So the simplest system to be talking about would be some sort of container full of helium, like a balloon full of helium, or maybe a metal cylinder full of helium. Anyhow, molecules don't come any simpler than helium. you have one atom per molecule, what we call a monatomic gas. These molecules are always moving around inside their container. Okay, they shoot around. They're always just going bing, 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 because each molecule, well, helium atom in this case, is essentially a little microscopic projectile, and it just shoots across the container until it runs into the wall, and then it bounces off and shoots up this way until it bounces off another surface, comes down here, maybe it bounces off another helium atom, heads over this way. So it just does sort of a random walk all around everywhere. And as it moves, it has some kinetic energy, 1/2 mv squared. Just add up the kinetic energy of all the molecules inside the container, and that's its internal energy. Now, if you have a somewhat more complicated molecule, the next simplest molecule would be a diatomic molecule, like oxygen or carbon monoxide or something like that. There you have 2 atoms in the molecule. Now, in addition to the molecules moving around inside the container, those 2 atoms within the molecule vibrate back and forth. They behave as if they're connected by a little spring, and you've got some vibrational energy. In addition, you can also get rotational energy as the 2 atoms tumble end over end at the same time that they're moving across the container, at the same time that they're vibrating. Add all of that up, and that's the internal energy of a balloon full of air instead of helium. And, you know, with even more complicated systems, it gets even more complicated. But, well, to summarize it all up, add the energy of the molecules. What does not count as part of the internal energy is if you take your helium balloon and, for example, give it a ride in an elevator. That is an external type of energy, okay? So that's what's meant by the internal energy. Q, I'll label all this as soon as I get the whole equation written down, but that's the same thing that Q stood for in physics 131. That's the quantity of heat added to a system, as in Q equals mc delta T. Hopefully that sounds a little bit familiar. W for work. Now, the first law is just full of opportunities to make mistakes with plus and minus signs. I actually saw a textbook once that had the signs wrong in the first law. So if a textbook author can do it, you can do it. So being careful about what's supposed to be positive and negative. W, the work, is the work done on the system. If work is in fact being done by the system, W would be negative. Q is the amount of heat added to the system. If heat is in fact flowing out, Q would be negative. And as with delta anything, this is positive when it's an increase. Increase in the internal energy. Okay, so internal energy, in the case of a gas at least, is proportional to the temperature of the thing, the absolute temperature. If you double the internal energy, you're going to double the Kelvin temperature. With liquids and solids, things get more complicated because you've got the latent heat stored in bonds between molecules, and I talked about that last fall, how that you can put a mixture of ice and water on your kitchen stove and add a whole lot of heat to it, and the temperature will sit right there at 0 degrees the whole time. It's just the ice melts. So there's energy stored in the bonds between molecules. That, you put it in when you melt the ice, it comes out when you freeze the ice. But if it's a gas you're talking about, an ideal gas, or to a good approximation, any real gas, the internal energy is proportional to the temperature. So what this is basically saying is that there's two ways to change the temperature of something. You can either add heat to it, or you can do work on it. I think I may have told you this story once before, a few months ago, but there was that time that I was cutting the end off a metal rod with a hacksaw. And then after I finished and went to take the rod out of the vise, I grabbed right next to where I had just been cutting, and I burned my thumb that way. Now, no heat flowed. Remember, the definition of heat is energy that flows because of a temperature difference. Heat energy flows from hot places to cold places. My hacksaw started out at 0 degrees. The rod started out at 0 degrees. There was no heat that flowed. Q in this equation would be 0 in this example. Rather, I was doing work against friction with every stroke of the hacksaw. So by doing work on that rod, I increased its internal energy and therefore increased its temperature and therefore burned my thumb. If I'd cut the end off with an acetylene torch, that would have been heat flow. No work done. This would have been 0. This would have been something else, and that would have also raised the internal energy, and I might still have burned my thumb. Okay? So that's kind of the basic idea behind that. Next page. So as we work our way further down the handout here, internal energy can be changed two ways: if heat flows or if work is done. Now, cutting the end off a rod, oh boy, that seems more out of focus than usual. Can't get all the way through one of these recordings without complaining about the focus, you've probably noticed. Anyhow, internal energy can be changed in two ways. And heat flow, I'll get to that down at the bottom of the page. Let's talk about work for a minute. If you're cutting something with a hacksaw, it's just how hard did you push the saw times how far did you push the saw on each stroke, and work is the force times the distance. When you're talking about thermodynamics, more often than not, you're talking about a gas confined to a cylinder by a piston. People first started studying thermodynamics, maybe roughly 250 years ago, because the Industrial Revolution was getting going, and people were running factories and things with steam engines. And if you've got a large factory powered by a steam engine, that thing will burn a lot of coal over the course of an entire year, which is to say it'll burn a lot of money over the course of a year. So if somebody can figure out a way to make a more efficient steam engine so that it didn't burn as much coal to do the same work, yeah, you could probably make a lot of money that way. So that's called incentive. And people started studying this sort of thing. And well, of course, today there's many different types of engines, but they all are governed by these laws of thermodynamics, as are any other system that has heat flowing through it, like a heat pump, such as an air conditioner. But whether it's some old-fashioned steam engine, or whether it's the gasoline engine in your car. Piston engines are still a very commonplace thing today, although there are other types, like, the jet engines on an airplane, for example, don't have any pistons. But, well, probably the best example to keep in mind as we go through this is a plain 100 years ago type steam engine. Because like most obsolete technology, it's simpler than the way we do things today. If you have a gasoline engine, you've got this flame front advancing across the air-fuel mixture as it burns, and you've got a gradient in the temperature, and you've got a gradient in the pressure, and with a steam engine, you've just got a cylinder full of steam, which has, well, maybe not perfectly uniform, but a fairly uniform temperature and pressure, and it's just a simpler, more well-behaved system to be talking about. So you've got this gas, steam perhaps, and let's say it's pushing this piston outward, okay? Now, if we want to talk about the work done on the system, that would be the work done on the system by this piston here. It's all seen in cross-section, of course. And so that would be the work done by this force that comes from the piston. Basically, because of the gas pressure, the gas pushes on the piston, and the piston pushes back on the gas. It's Newton's third law, action and reaction. So the gas is doing some work, turning the wheels of your car or whatever, by pushing this piston outward, and the piston is exerting this force on it while it does that. From Physics 131, the work done, we're going to consider just an infinitesimally small motion of the piston so that we can talk about a constant force, okay? As the gas expands, the pressure drops. As the pressure drops, the force gets smaller. But if you take the limit as this distance approaches zero, then the amount that the force changes will also approach zero. So in that limit, we can say that the work done equals the force times the distance. There's a cosine factor, of course. Work is actually the dot product of the force and the displacement. But in this case, well, I was about to say the cosine factor equals 1 because all it can, the piston can't move off at some weird angle. It has to follow the cylinder. But actually, it's 180 degrees because notice that the displacement is toward the right, but the force is toward the left. The two vectors make a 180-degree angle, which creates a minus sign. And so I'm going to introduce a factor of A over A. That's just like multiplying by 1. I can do that. A, like it says, is the area of the piston, meaning the area in contact with the gas on the end here. I have noticed a tendency students have to go to their formula sheet. Oh, I need a formula for this. Here it is, the area of a cylinder. Pistons are cylindrical. That gives you the lateral surface area. That's the side. If you're going to calculate the pressure, that's the force divided by the area over which the force is distributed. That's the area on the end here, the area in contact with the gas. So that would be a pi r squared kind of thing, not 2 pi r times the length of it. So piston's area means the area on the end, the area that the gas is pushing on. Introduce A over A, move things around a little bit. Force per unit area, that's the pressure, the gas pressure. And A times dx, well, that would be the volume of this little pancake of a cylindrical volume right here. the small volume between the pistons before position and the after position, that little bit from there to there, which would be the amount that the volume of the gas has changed as the piston moved. We'll call that dV for the change in the volume. So work is basically force times distance, but in a system like this, people find it more useful to talk about things like pressure and volume than force and distance. So you make some substitutions and can show that the work done on the gas is minus, I'm off the edge of my picture. So the work done on the gas is minus PdV. Now there are other physics books that are written the other way around. Instead of having the work done on the system, they have the work done by the system, and then the first law would have a minus here instead of a plus, and then this would be PdV instead of minus PdV, but I'm going to play along with the way our particular textbook is written. And so that's the work, assuming that you're talking about work done by an expanding gas. Where the work comes from is, well, you know, you've got the internal energy from the molecules moving around in there. The molecules are constantly bombarding the end of the piston. If the piston is moving outward, those molecules will lose energy in the collision, okay? On the other hand, if the piston is being shoved inward, compressing the gas, then the molecules will gain energy from the collisions. Consider a collision between two cars. I think everybody understands that if you are playing with your phone and don't realize that you're gaining on the car in front of you and drive into the back of it, that you receive a significantly smaller jolt from the collision than if you're playing with your phone, wander into the other lane, and get into a head-on collision with somebody coming the other way, okay? Same thing here. If you've got a gas molecule going this way and it comes up on the piston from behind, that gas molecule does not receive nearly as much of a jolt as if the gas molecule and the piston get in a head-on collision. So the larger impulse that the molecule would receive in a head-on collision makes it go faster after the collision, whereas the other way, it just, the force from the collision helps to push the piston outward, and the molecule loses speed when it bounces off of it. So an expanding gas loses energy in the form of work. A gas that's being compressed gains energy from the work done. Well, let's see. Work equals minus PdV. I was going to write down a couple. I have to write something down from every now and then to make you copy it and keep you awake. So it says there on in that note packet that the work done in an infinitesimal expansion is minus P times dV. Well, of course, if all it moves is an infinitesimal distance, your car isn't going to go very far. If the piston moves a significant distance down the cylinder, you have to add up all these small contributions and get the total for its entire displacement. So the total work, W as opposed to dW, would come from integrating that from whatever the initial volume was to whatever the final volume is, P times dV. Now, I'm sure you've been told more than once in your calculus class the geometric meaning of an integral is it's the area under the curve. So if you draw a graph of pressure as a function of volume, this integral would be the area underneath the curve on that graph. So area under the PV curve. There is such a thing as an isobaric process, which means a process where the pressure remains constant. If that's the case, okay, in that special case, there would be no need to resort to infinitesimals. It would just be P times delta V. Or if you want to think of this as the general expression, and then what happens in the special case where P is constant, if P is constant, you can take it out in front of the integral, which leaves you with just the integral of dV. And when you evaluate that at the limits of integration, you've got V final minus V initial, P times delta V, as I said. So minus P times delta V if the pressure is constant. And I think most or possibly all of that is on your formula sheet. A couple of examples that make use of that. For kind of a warm-up, this example I do also in my algebra trig-based class. The second one I do not. But number one has been rigged up so that you can find the area under the curve without having to do any integration. It's just, you know, an integral is where you have basically an infinite number of infinitely narrow rectangles under the curve and you add up all their areas. Well, here I can just have two rectangles of finite width, and that'll give me the area underneath this thing. So find the work done. The area under the curve would be the area of this rectangle added to the area of this rectangle, and I should be careful what I point at that with because I'm writing all over it. Area of a rectangle is the length times the width. Okay, so the length of this one is 300,000 pascals, and its width is 0.02 of a cubic meter. And this rectangle has a length of 200,000 pascals, and its width is 0.025 of a cubic meter. And so that's the idea. I'll just write down the details for you. So work again, this is the length, this is the width of the one rectangle, this is the length, this is the width of the other rectangle. Put them together and you have the area under the curve. One little detail that I didn't mention before, delta V is negative because the volume is decreasing. Delta V, like delta anything else, means final minus initial. So if you look at the direction of the little arrows I drew on the graph, the gas inside this cylinder here starts out in this state. The word state just refers to what set of conditions is the gas being subjected to, the pressure, the volume, the temperature, all of that. So it starts out in this state and moves to that state. And so this is final, this is initial, that's the order you have to subtract them in, which makes delta V come out negative because the volume is decreasing. And then it's the same story with the other term. Three times 10 to the fifth pascals. A pascal is equivalent to a Newton per square meter. Force, a unit of force divided by a unit of area is a unit of pressure. And so that times that times that. The minus signs cancel. You're going to get a positive answer. 1.10 times 10 to the fourth. Work is measured in joules. Number 2. Well, 13-2. This not only serves as an example, but also as a derivation of a formula that's on your formula sheet. So it's kind of like I'm taking care of two things at once. This is one of those more general type problems where you don't have specific numbers. You're just going to calculate something in terms of a bunch of letters. So find the formula for the work done in a constant temperature process. It's known as an isothermal process. Well, I can tell you another time how you would realistically go about accomplishing an isothermal process. For now, let's just run through it. So if the gas expands isothermally, the pressure is not going to remain constant. More details on that later in this section. If the pressure is not remaining constant, then you can't just get away with P times delta V. You have to integrate. So the work done is going to be the integral, well, almost forgot the minus, from the initial volume to the final volume of P dV. Hopefully none of you are still so naive as to think that the integral of P dV would be 1/2 P squared. That would be the integral of P dP. We have to get everything in terms of the same variable before we can integrate it. And more often than not, in this corner of the subject, you know, in thermodynamics, when you're looking for a substitution, more often than not, it comes from PV equals nRT. And that's what I'm going to do in this case, to get a substitution for the pressure. So minus the integral of V initial to V final. If PV is equal to nRT, it follows that P equals nRT divided by V. So write the thing that's equal to P where the P used to be. Now, in general, this would not have improved things any. I would have just swapped out one variable for another one, T, and I'd still have two variables. But remember, the question is work done in an isothermal process. We're considering the special case where the temperature is a constant. If T is a constant, you can slide it out in front. You know, it's like it's the same thing as if that was a 12 or something like that. You can just take that out in front of the integral and get it out of the way where it won't bother you anymore. So N is also a constant. N is the number of moles that will not change unless the cylinder leaks. R is the universal constant in the gas law. That obviously is a constant. T is a constant because it's an isothermal process. Which leaves us with the integral of dV over V. So we've got minus nRT times the log of V from, of course, you have to evaluate it at the limits. And that can be made more compact by making use of that product or that property of logarithms that says the difference of the logs is equal to the log of the quotient. So that's, and there's a little section in your reference handout that has properties of logarithms in it. Oh, you know what? I did something else first. As I look over there, yeah, that's a good idea. Let's get rid of this annoying minus sign. So you distribute the minus sign across both terms. The initial becomes positive and the final becomes negative, like this. Now I'll do the thing where you combine them, and this will be the answer. So that is the work done in an isothermal process. The question told you the initial final volume and all this other stuff. You could drop the numbers in there, and that would give you a specific answer for that specific case. I wonder what it says next. Okay, so we've done the two examples. That's all some stuff that relates to the W term in the first law. Now some stuff that relates to the Q term, the heat, in the second law. From physics 131, heat is the energy which flows due to a temperature difference. I already said that a little while ago. Q equals mc delta T, where C is the specific heat of the property of the material. Hopefully it sounds familiar. We did a lab about that and everything. Back when we were doing real labs. So when you're dealing with a gas, okay, the specific heat last fall was the energy per unit mass per degree, which is a fine way to do it when you're talking about liquids or solids. But when you're dealing with a gas, really the behavior of gases depends more on how many moles you've got than how many kilograms. So to indicate the difference, let's use a capital C instead of a little c. Little c is the specific heat that's measured on a per kilogram basis or a per gram basis. Capital C is when you do the same thing, but per mole rather than per kilogram. Molar heat capacity or molar specific heat. Different authors use slightly different names for it, which makes our equation Q equals NC delta T if you're going to describe how much gas is present with the number of moles instead of with the mass. If you're old school, calories per mole per degree, or if you want to stick with SI units, joules per mole per degree. Now, things get more complicated. with liquids and solids, the specific heat is the specific heat. You just got a number that you look up in a table, and that's pretty much the end of the story, a number somebody experimentally measured. With a gas, the specific heat depends on what the gas is doing as you're adding the heat. The two cases that people seem to want to talk about the most are what is the specific heat if you're keeping the volume of the gas constant? What is the specific heat if you're keeping the pressure of the gas constant? This one is more than that one. Let me explain why. We've got, I'm going to write down the first law again so we can kind of keep that in mind while I'm talking about this stuff. That was the change in the internal energy equals Q plus W. So once again, the first law. So first of all, if you're going to, well, let's consider a cylinder like you'd have in the engine of a car, for example, a cylinder with a piston in it, seen here in a cross-sectional view. At a constant, well, you're going to add some heat to this, okay? You're going to hold a propane torch where it blows on it, or throw it in some boiling water or something. At a constant volume, first of all, that means the piston doesn't move. Somebody shot your engine full of super glue, and as you add the heat, the piston stays in exactly the same place the whole time. Well, if the piston doesn't move, then it's not going to do any work, okay? Or in terms of the formula, you know, P times delta V is 0. So at a constant volume, no work is done. Remember the internal energy. The internal energy is proportional to the temperature in a gas, an ideal gas. So delta E is proportional to delta T. And if this is 0, here's where I get to the point. If this is 0, all of the heat goes into raising the temperature. On the other hand, if it's a constant pressure process, the way you have a constant pressure process is instead of shooting the thing full of super glue, let's keep a fixed, here, W for weight. Maybe you set, I don't know, 5 newtons on top of there. And so maybe, well, however much weight that is, you're keeping a constant force bearing against the area of this piston. So since since pressure is force per unit area, if you always have the same force distributed over the same area, that's going to keep the pressure constant. If you go adding heat to this, so the temperature goes up, that will make the gas expand, which would lift the weight up. By the same token, if heat flows out, the gas will contract, the weight comes down. So anyhow, as you add your heat, the gas expands. That lifts the weight up higher. When the weight's up here, it has more potential energy than it had when it was down there, okay? You're doing work lifting that weight. So in the constant pressure case, the heat you add goes to a couple of things. Part of the heat goes into raising the temperature. Part of the heat goes into lifting the weight. At a constant volume, all of the heat goes into raising the temperature. At a constant pressure, only part of the heat goes into raising the temperature. Therefore, you have to add more heat to get the same temperature change when it's a constant pressure than you would at a constant volume. And that's why the specific heat at a constant pressure is more than the specific heat at a constant volume. And that is probably somewhere in the next few sentences on this handout here. Let's see. No, maybe it's not. But now you know. The relationship between internal energy and temperature. If I remember right, I'll be honest with you, I haven't looked that closely at the textbook for a while, but you know, physics doesn't change. But if I remember right, there's an entire chapter in the book on the kinetic theory of gases, which is a good thing to know about. It's just there's only so many weeks in a semester, and I can only cover so many topics, and the kinetic theory turns out to be one of the things that I condense down from a chapter into about one sentence. But the basic idea is that you consider the molecules moving around inside your container to be a mechanical system, and you apply the laws of mechanics, such as the impulse and momentum theorem. So using the methods I covered in Physics 131, you can get you also have to apply some statistical methods because the molecules are not all moving at the same speed. There's a whole distribution of speeds, and you have to deal with that. But from using the impulse and momentum principle that F times delta T equals the change in the momentum, you can get an expression for, you know, if you've got a gas molecule moving across here and it bounces off the wall of the cylinder, you can get an expression for the force delivered during the collision, how that relates to the change in the velocity. Well, if you add up the forces from all the collisions from the many molecules and then divide it by the area which those collisions took place in, that gives you an expression for the pressure. The impulse momentum theorem relates that to the velocity. You know, on the other side of the equals sign, you've got mass times velocity. It relates it to the speed of the molecules, which from there you can get to the kinetic energy and blah, 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 blah. Eventually you end up with an expression for the average kinetic energy per molecule. 1/2 mv squared average. If it's a monatomic gas like helium or argon, one of those, 3/2 kT, where K is Boltzmann's constant. Maybe I should, well, I'm not going to test you on this. This is just something I'm throwing in as a little footnote. But if anybody cares, K is Boltzmann's constant, which you can look up in our textbook or any sort of standard reference like that. If it's not a monatomic gas, if it's something like oxygen or methane or carbon dioxide or something, then it changes this coefficient here. It's no longer 3/2, but the rest of it's the same, okay? So the average kinetic energy per molecule is some number times kT. Well, then this is the average energy of one molecule. If you add that up for all the molecules in the container, then the total would be this expression that's printed here in the handout, okay? Internal energy of a monatomic gas, 1 atom per molecule. There's the same factor of 3/2. There's the absolute temperature. And the number of molecules and Boltzmann's constant get absorbed into the N times R factor. So that's something like helium or argon or neon. If it's methane, well, the situation, again, I'm summarizing a whole chapter here, but it turns out that it's some other constant. Once again, it's the number of moles, N, times the temperature change. Well, here I was talking about E, here I'm talking about delta E. So it becomes delta T. But you've got the number of moles, you got the temperature, and instead of 3/2 R, you have some other constant. And what is that constant? Well, we can evaluate it just by considering a special case. Let's think for a moment about a constant volume process. So if the volume is constant, then the work, as I've already mentioned before, I think, work is negative P delta V. If the volume's constant, the change in volume is 0, no work is done. If the pistons don't move, the wheels on your car don't turn. So in that case, well, since it's a constant volume process, Q, well, in general, Q equals NC delta T. If it's a constant volume process, you would use the constant volume specific heat. Now, this is just a special case, but if you, this thing here is supposed to be true in general. Change in internal energy equals N times some constant times delta T. Compare that to this. There's the N, there's the delta T. The thing that is called a constant here must be CV. So for any process, constant pressure, constant volume, any other kind of thing, and also it doesn't have to be a monatomic gas. For any kind of gas, for any process, for any ideal gas, for any kind of process, whether it's the pressure that's constant or the volume or whatever, the change in internal energy is proportional to the change in its temperature, and the proportionality constant between them involves the constant volume molar specific heat. Now, if it's a monatomic gas, helium or argon or one of those, as it mentions a little further up the page, it's shown from the kinetic theory of gases that the change in internal energy is 3/2 nR times delta T. Well, if you compare this to that, the constant volume molar specific heat, it's kind of a mouthful, isn't it, for a monatomic gas is 3/2 times the gas law constant. A theoretical prediction which is borne out experimentally. There's a table of these things toward the back of your reference handout, and if you go there and look at it, you'll find that helium, argon, neon, all of those monatomic gases have pretty much the same molar specific heat, which is equal to pretty close to 3/2 times R. So the theory and the experiment match up with each other. Oh, this is just about one class's worth of stuff, I guess. The last recording from section 12 ran a little on the long side, but that's okay. If you don't want to watch that much at once, it's a video. You can stop it and come back the next day. But I'll stop this one here and pick this story up in the next video. Pick it up where I left off.